In lecture 84 and 85, we'd just like to cover the tensor, second rank tensor of thermal expansion. And we've already set up in previous lectures most of this because we talked about the harmonic potential and about how in the case of all of our other properties dealing with stress and strain and force and all this sort of thing, we've assumed a harmonic potential, which means that we end up with springs connecting atoms. Thermal expansion comes from the imperfection of that model. So let's talk about that. So again, we've already discussed this, but if we were to look at bonding between molecules, or in this particular case, we're extending that to a model of having atoms in a solid bond to each other, they follow the same kind uh, of curve, where here's the bonding energy, and this is the distance between, atoms. Let's call it, x minus x0. And what we saw was that, of course, you get repulsion when the atoms get very close, and then you have Coulombic attraction, which occurs over a longer distance. And so those two opposing forces balance at some bonding distance, x0, right? And we had pointed out that right down here at the bottom, small deviations, the amazing thing is this Coulombic force, which deals with 1 over the radius, and then this repulsion force, which is tricky because it's really Pauli exclusion principle if you think about it, because you're trying to force electrons into the same space in a small volume, but they can't, right? They have to have different quantum numbers. So it's one way to look at this, or you know, a more simplistic way of kind of saying this, so that's not really 100% accurate, is say, well, it's nuclear repulsion, but that implies it's Coulombic nuclear repulsion, and it's actually, more detailed than that because of what I just said. So actually, there's just some very rapidly rising, extra energy that goes in if you try to force two atoms too close together. And of course, the thing that's pulling them in is this Coulombic one. And then they balance, and amazingly enough, down at the bottom, this is estimated to be a parabola. And of course, the parabola we mentioned, if E is parabolic in distance, you take the derivative, force is dE dr. And so you end up with a force being linear in x. And that, of course, is like a spring, right? And so that's how we get a lot of our mechanical properties being represented by this sort of, in the elastic properties being linear. Like that's how we derived the strain tensor, right? U is linearly related to epsilon and x, right? So E or epsilon is the proportionality in which this constant that appears in the F equals kx, is in that essentially in epsilon throughCijk, which we haven't talked about yet, responding to sigma. So it's all related, but here thermal expansion is actually about the imperfection of this. Now imagine as we heat this material up, my atom vibrations. So let's actually draw this first. So in the case of the red here, I can imagine I've got these ions, positive cores with these clouds around them, and I've got some equilibrium distance, and I'm able to represent this with a spring. And as I heat this up with temperature, this thing vibrates more and more, right? And so I start to deviate and bounce further and further out. Now, as I heat this thing up and my mean atom distance starts to spread out over this area, I'm going to start picking up the fact that here and here we are not parabolic anymore. And of course, that's why we have thermal expansion. If everything expanded evenly, right, the net displacement would be zero. I'd have volume change only, and life would be much simpler. But of course, it's not really that way. It gets distorted, right? And this actually moves. So what happens is, uh, as this curve goes up, and you can see it even just the way I drew it, as we start to sample higher up on this curve, right? This has a very sharp rise, right? So what's going to happen is it's going to sample more out here. So you can just see, just in this curve, that if I'm going to sample on this energy curve higher and higher points on it, and there's states that can be higher up here, the mean distance between atoms is going to increase because this is flatter on this side. And so if I average over here, and there's more and more points way out here, you can see it up here, right? This is going up, but it's not going up that fast. Way over here, I've got all these points I'm averaging over here. You could tell that the hotter it gets, the more that, you know, this average bond distance is going to go to the right. So how do we do that mathematically? Well, actually, it's not too difficult because the potential well there, you know, we had modeled as having some parabolic shape. Well, mathematicians call this expansion about that point, but engineers think about it physically. But if we think about it there, let's just call this some proportionality to a cube term. And then there is some other proportionality to a fourth term. Okay? So if you think about this from a potential point of view, let's think about it. This used to be described in the bottom as a parabola with cx squared. But, you know, as I go up here, right, the potential won't be where I think it's going to be, right? It's going to be less than I thought it was going to be, right? So this is kind of the asymmetric term, right? Because it's saying, look, you thought the potential was going to be much higher. If this was tighter, a tighter parabola, right, and I were to go up in energy potential, right, then, you know, I would expect that I would have more states going up faster. If I start to have an asymmetric thing like this, what happens is my overall potential won't be as high as I would have thought if I had a nice sharp well. So in a way, this is the asymmetric part, the cubic part, and it should be less because my potential is going to be less than I thought than if it were a cube. Finally, I need a term that, even though that's working, I need to represent this kind of eventual, you know, very flattening. So it's very, very large x. I want this thing to have some very slow, you know, function out here that's kind of really, you know, flattening out. And you can think about this other term out here as that. So, but anyway, we can now ask the question, you know, what is the average x, or more importantly, x bar in our notation, right? So let's look at px first, which is the probability. And if you guys have taken physics class as a class or math class, you know, this is essentially the probability of finding the system in a particular state, right? And that is proportional to, if we're going to assume Boltzmann, which is a good assumption here, that is always the so anytime you have potential like that and you want to ask what's the probability for finding something in a particular state, assuming that they're bosons, which means that you can have as many, and atoms are here, you can have as many of these units in any state you want, then the probability is going to be just this Boltzmann distribution with the energy of the potential in there divided by kT. So the classic definition of an average then is the thing you're averaging times the probability of finding it in those states integrated over x, which is essentially sampling over all the probability from minus infinity to infinity. So we have to integrate all across here and find out what the average x bar is for all the points that would be occupied given, particular energy that's distributing. Now, this itself has some number. If I just integrate it over this, so I have to normalize it because remember that this distribution thing, I said it's proportional, but I haven't put anything out front here. And so there's two ways to do this. You could normalize this probability ahead of time by integrating over minus infinity to infinity and set this equal to 1, and then you wouldn't need this term. Or to make it absolutely clear so that you don't necessarily have this thing like we've done here. It's not normalized. We haven't integrated that to equal 1 over minus infinity to infinity. So we haven't put any coefficients in there. You can actually, without having to solve that problem, initially just say, well, I'm going to put that in, that the distribution itself, has some normalization that has to happen, but I'll just stick it right in here. So this is simply the, again, I could make sure that integrated over this is 1, in which case I can just drop it out. But here I'm just putting it in for completion. So anytime you see this, that's just the normalization part. It's just because the thing that we're putting in here, the Boltzmann distribution, we want to make sure it doesn't add to this x bar because it's just the weighting of the different x's, how common a certain x will be. And that weighting has to be, normalized and put in the bottom. So if you solve that, and again, the way you solve that is that, fortunately, these Boltzmann distribution, if you look up in integration tables, they're very, very common, so they're actually easy to solve. In our case, v has all these different terms, but it turns out when you put v in here, and if you were to break this up into separate integrals, those are very common because if you put v into the exponent, remember that when I multiply exponents times each other, the exponents get added. So the reverse is here. I can split this up into different integrals. And then each one of these integrals, this with an x cubed, x4, x5, x squared, x third, x fourth with the x out front, end up being standard integrals that you can look up and save you time. And what that comes out to is if you do that exercise, as you know, you always get these square roots of pi's and those kinds of minus infinity to infinite integrals. And you get a lot of kT's to the 3/2 as well. And that's why, when you do statistical mechanics and you have, statistical thermodynamics, you have translation partition functions, and they all have kT to the 3/2. Comes from that. And so if you were to look at all that stuff, and so you end up with something that you should end up with. X bar, which is a single direction in Cartesian space, has a linear dependence on temperature. So as temperature goes up, x bar goes up by this constant, and we tend to call this alpha. Okay. And it also has the, remember that C, just to remind you, C was connected to the parabolic x squared, and that G was connected to the x cubed. So what's very interesting about this is it makes sense, right? Which is good, which means we did our work correctly, because C squared, the larger the C, remember in this, it was out front, cx squared, right? The larger C, the stronger the bond. So the stronger the bond, the smaller the x bar for a given temperature. So if C becomes very large, this becomes a very tiny number, which means that as an increased temperature, x bar doesn't increase that fast, right? So that makes sense, because if I have very stiff material, very strong bonding, very deep potential well, which makes it sharp, C is large, right? The other thing is that G was the new part that we've really added to give us that asymmetry. So you can kind of see that G, which was connected to x cubed, is the anharmonic part, the part that is not, with x squared. And you can see here that if we were to set G to 0 so that we have a pure parabola, actually x bar would go to 0. And so, if you had no, and 0, remember here, is essentially being at x0, right? Because it's a differential part, right? So this is x bar being, some distance away from the x0. So this all makes sense, right? So that's thermal expansion, and that's the origin of it. And we will now go on and just talk about very quickly in the next lecture thermal expansion tensor.